Good morning, this is Dr. Jingbo Louise Liu. We are going to finish your chapter 5, Ideal Gases and the Kinetic Molecular Theory. So today we are going to practice more about the application of ideal gas law and then show you some behaviors about the gases in the mixtures. And then we show you the kinetic molecular theory, which is a model for you to use to describe the gas behavior. And then the last topic will be about the ideal gas motion. We are going to learn Ram's law. The last topic about real gases, we are not going to discuss it, and I list several key natures about the adjustment of your ideal gas law to describe the real gas behavior. So let's move on to look at this first problem. So we are going to try to apply the pressure-temperature relationship. So what you have a steel tank which used for the fuel delivery. This steel tank is fitted with the safety valve, which is going to be open whenever the internal pressure exceeds 1,000 torr. Is filled with methane at 23 Celsius and the pressure was 0.991 atm. And then this steel tank has been placed in a boiling water at exactly 100 Celsius. The question is, will this safety valve open? The plan, we must determine whether the pressure at high temperature is going to be exceeded the 1.0 times 10 to the power 3 torr. So therefore, you are going to use the relationship between the pressure and the temperature. So first of all, you are going to make sure you convert the pressure to the same unit. If you have torr, atm, make sure you keep it consistent. The second part, you need to convert the temperature from Celsius to Kelvin. And then you are going to apply the relationship between pressure and the temperature, the solution. Because you have the steel tank, which has a fixed volume, meaning the volume is fixed, you introduce filled with a certain amount of methane, meaning the moles is also filled. Therefore, the moles and the volume both constant. So your pressure 1, 0.99 atm. Temperature 1, 23 Celsius. Pressure 2 is what you need to determine. Temperature 2, 100 Celsius. So convert your temperature into Kelvin from Celsius. Convert atm to torr. So atm to torr conversion we know from 0.991 atm by multiplied by 760, convert atm to torr. And then you use your P1, P2 related to the temperature 1, temperature 2. So you cross out the same quantity V1, V2, and 1, V2. So you have P1 equals T1 equals P2 divided by T2. Your P2 can be calculated by using P1 times T2 over T1. So therefore, you calculate the new pressure. My calculation is 949 torr. You are going to do the comparison. Because this value is smaller than 1,000 torr, therefore your safety valve will not open. That's your first question about the pressure-temperature relationship. Followed by, I want to show you about the mixture of gases. In the real situation, the gas is existing as a mixture such as the atmosphere. The gases mix homogeneously in any proportion. Each gas in the mixture behaves as if it were the only gas present, meaning the other gases does not interrupt the gas which you are studying, such as you have an atmosphere, you have oxygen, nitrogen. Oxygen, nitrogen, they act as if by itself. The second point is about pressure, which is called partial pressure. This partial pressure is the pressure exerted by each gas in the mixture. And then you are going to use Dalton's law of partial pressure to determine the total pressure or vice versa. Dalton's law of partial pressures states the total pressure in the mixture is a sum of partial pressures of the component gas, meaning the total pressure equals P1 plus P2 plus P3 plus P4, etc., etc. On the other hand, the partial pressure of the gas is proportional to the mole fraction of that gas. If you have gas A, the total pressure can be measured. The mole fraction of the gas A can be calculated. And then PA equals XA times P total. This PA represents the partial pressure for your gas A. For example, for your gas oxygen. And XA is the mole fraction of the gas A. P total is the total pressure for your mixture. This XA, called mole fraction, can be calculated using the moles of this A divided by the total moles. Let's try an example. Applying Dalton's law of partial pressures. Assume you are studying the oxygen uptake by the muscles at high altitude. You are going to prepare the atmosphere, which is composed of 79% of nitrogen in moles, 79 mole percent of nitrogen, 79 moles of nitrogen, 17 moles of oxygen, 16, and 4 moles percent of oxygen, 18. Oxygen 18, oxygen 16, they are the isotopes. Oxygen 18 usually can be used to measure and determine the oxygen uptake. So the total pressure of this mixture is determined to be 0.75 atm to simulate the high altitude. What I want everybody to do to calculate the mole fraction and the partial pressure of oxygen 18 in this mixture. What's your plan? First of all, you are going to find the oxygen mole fraction. You have oxygen 18, which you have 4 mole percent. You convert your mole percentage to the fraction. You're simply using this number divided by 100. And then your mole fraction determined, you use your mole fraction multiplied by the total pressure for the mixture to derive the partial pressure for your oxygen 18. Your solution. Step 1. Determine the mole fraction. You're simply using this 4 divided by 100%. So you have 0.04. And then you are going to use your mole fraction multiplied by your total pressure. Mole fraction is 0.04. Total pressure has been determined 0.75 atm. So you can determine the partial pressure for the oxygen 18. Similarly, you can determine the partial pressure for your oxygen 16 and for your nitrogen. You again simply convert these mole fractions, this mole percent to a mole fraction. So move your decimal places to the front by 2. So that's how you determine the partial pressures if you know the total and the mole fraction. And then we are going to determine what is the key points of the kinetic molecular theory. Again, the kinetic molecular theory is a model for you to describe the gas behavior, you totally have 3 postulates. First one, gas particles are so small with the large spaces between them. The volume of each individual gas particles is so little tiny compared to the total volume of the gas. Therefore, you assume the gas molecules has 0 volume. The volume of your gas molecules are 0. Postulate 2. The gas particles are in a constant, random, straight line motion, except when they collide with each other, or the gas molecules collide with the container walls. Otherwise, the gas particles move constantly, randomly in a straight line. The third postulate, whenever this collision occurs, the collisions are elastic, meaning the colliding particles exchange energies but do not lose energy due to the friction. The total kinetic energy is constant. The total kinetic energy for your whole system is a constant. Between the collisions, the particles do not influence each other by attraction or repulsion forces. Obviously, these 3 points are the approximation. The real gases, each individual molecule, they do have the volume. You need to correct it, to adjust it. And also, particles, gas molecules, they do affect on each other. So how do you adjust? So we are going to give you an equation for the real gas law. So in that case, you can further study, further evaluate it. And it is also known the kinetic energy is directly proportional to the mass and directly proportional to the speed to the square 2. So usually the delta E K, the kinetic energy changes equals to 1/2 multiplied by c multiplied by velocity to the power 2 at a given temperature. All the gases in the sample at the given temperature, as long as they have the same mass, you assume they have the same average kinetic energy. The kinetic energy depends on both mass and the speed or velocity of your particle. At the same temperature, if you have larger particles, those larger or heavier particles move slower than the lighter ones. For example, if you have oxygen, nitrogen, water molecule, helium, and hydrogens, so which one moves slower? So the oxygen molecule, generally speaking, moves slower than the smaller ones, hydrogen. And also your kinetic energy is related to the speed, and the molar mass and the molecular speed, they also have relationship. So if you take a look at this one, so your relative number of the nitrogen molecules, for example, with the speed, you have different speeds. What we also found with the temperature increase, so you have this velocity for the same molecule nitrogen. If you increase your temperature, this is lower temperature, a little higher temperature, much higher temperature. With the temperature increase, the speed for the gas molecule moves faster. So speed also increases. This is essentially about the kinetic energy related to the mass and the speed, and the relationship between the molar mass and the molecular speed. Also, the relationship between the molecular speed and the temperature. The very last point is about the motion of gases. Your gas can diffuse. Your gas also subject to a special motion which is called effusion. The effusion is the process by which a gas escapes through a very small hole in its container into an evacuated space. Imagine I have this diagram. So on your right hand side container, so you are going to evacuate the gas. There's no more gases. And then in between, you have this separator. So you have little tiny hole. If you allow these two sides connecting to each other, what's going to happen? Some gas molecule is going to moving from the left hand side to your right hand side container. This process is called effusion. The effusion can be measured or calculated using Graham's law. The Graham's law of effusion states that the rate of the effusion of your gas is inversely proportional to the square root of its molar mass, meaning the lighter the gas moves much more quickly. And also, the higher the rate of effusion, usually so is for the smaller molecule gases at the same temperature. So this is the effusion rate calculation. So effusion rate, so you can use alpha to represent it, is directly proportional to the square root of the molar mass. You can write down effusion rate equals 1 divided by square root of your molar mass. So we are going to show you how to do the calculation. So let's look at the right hand side graph again. Imagine you have two colors. One is black colored, another is red colored. The red colored represent the larger molecule, the black color represents the smaller molecule. So the lighter molecule moves first, moves faster than the red one. And also when this effusion is going to stop whenever the equilibrium is reached, meaning both containers is going to have the same pressure. So your effusion has no change, but from molecular perspective, the molecules still effuse from one side to another, but the pressure stays the same. So let's practice the Graham's law of effusion. So your problem is a mixture of helium, He, and methane, CH4. Both of these gases are placed in an apparatus. So to allow the effusion to occur, calculate the rate ratio of the effusion rates for the two gases. You have your methane, you have your helium. I want to calculate the effusion rate ratio between these two gases. Your plan. Your effusion rate is inversely proportional to the square root of the molar mass. So therefore, we can calculate the molar mass for each substances. If you have the atom, just find the atomic mass. And then you take the square root to determine the effusion rate. And then you take the ratio of the effusion rate. Your solution. Step 1. Calculate the molar mass of methane. So carbon 12.01, hydrogen 1.008 multiplied by 4. The calculation is 16.04 grams per mole. Your helium 4.003 grams per mole. So what you are going to do, you calculate your helium rate. Helium rate equals 1 divided by square root of the 4.03. And your methane equals to the square 1 divided by square root of your 16.4. So you can simplify it to this equation. So the calculation is the ratio between the rate of helium and the rate of methane is approximately 2. Helium is much smaller, meaning moves much faster. Methane is a bigger molecule, moves slower. So this is essentially about the Graham's law to determine the effusion, followed by I have several take-home messages for all of you. The first one is about real gas. Your real gas do have the deviations from ideal behavior. In your real gas, so that kinetic molecular model describes the behavior only for ideal gases. Real gas deviates from these behaviors. In which way? Number one, real gas have real volume. Each of the gas particles are not a point only of mass, but they do have volume. Gas molecules have volume and mass, even though they are very little tiny. Real gases do experience attraction from the others and repulsion forces from the other particles. Real gases deviate most from the ideal gas at the temperature which is low, pressure which is high. Therefore, we have another equation called the van der Waals equation. Van der Waals equation is showed as this way, meaning your pressure must be corrected, your volume must be adjusted. Therefore, you have two different constant values, A and B. A and B are the factors, A related to the influence of attraction, B related to the particle volumes. And we also have some numbers for you about A and B in case in your study you need it. And we have a couple more examples about calculation. We call the ideal gas stoichiometry, and based on the ideal gas laws, you are going to do more calculation to determine the moles, the pressure, temperature of the different gases. I have a couple more examples. I'll leave it for all to further study by yourself. That's it for all. Take care, stay safe, and stay